Well, hello and welcome to the 22nd lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So, over the past few lectures we were discussing a very important topic, two very important topics about in behavioral theory of systems, namely controllability and observability, right. So, if there is a behavior which is given by a kernel representation which looks like this, yeah, where R xi is a polynomial matrix of size G cross Q. If we assume without loss of generality that R xi is full row rank, right, then controllability, as we have seen, controllability or patchability of arbitrary pairs of trajectories in the behavior B, controllability of B is equivalent to this matrix R xi being factor left prime, which is also the same as saying that the rank of this matrix R lambda, which is a constant matrix, is equal to G for all complex number lambda, right. That was controllability. There were in fact several equivalent conditions, necessary and sufficient conditions, out of which I specifically mentioned these two because this will be important for us as far as observability is concerned, right. So, for observability we saw that we need a partitioning of variables, yeah, into W1 and W2, right. So, what was this? So, suppose my behavior is given by behavioral equations which look like R1 xi acting on W1 plus R2 xi acting on W2 equal to 0. We are asking the question, is W1 observable from W2? So, we are asking the question whether is it possible to deduce W1 from W2, right. That is the basic understanding of observability. We were in the middle of proving these three implications for observability, and we said that because of the closed nature of this chain of arguments, we have necessary and sufficient conditions. Yeah. So, these are the three conditions that we were looking at, yeah, three implications that we were looking at. So, observable W1 is observable from W2 if this simple looking condition is satisfied, that whenever W2 is 0, W1 must be 0. Observability guarantees that this should be true. Why? Because of a very simple argument, as you can see, as we had proven in the last lecture, that if it is deduced from here, then if for a 0 W2 you have non-zero W1, right, then it's impossible to set up a map from W2 to W1, because in that case for one single W2 there might correspond there might be several W1s corresponding to the same W2. If that is the situation, then it's impossible to set up a map, because for a mapping to work, in order to derive W1 uniquely from W2, you need unique you need a unique relationship between W2 and W1. Yeah, one W2 cannot give rise to several W1s, then it's impossible to set up a map between from W2 to W1. It's impossible to deduce W1 from W2. Yeah, just think about this, that if for one single W2 there corresponds multiple W1s, W1, W1 hat and so on, then how will you set up this map? For this W2 you have several choice, and choice is not allowed here, because I need to deduce what W1 is from W2. So, there must be a unique, several different W2s can give rise to the same W1, that is not a problem. That is like a mapping which is not one to one, that is fine. But in order to even set up a map, you need a unique W1 to be associated with a given W2, right. If you can't do that, then you cannot set up a map between W2 and W1, right. That is the basic idea of the first condition of observability, right. but it is only it is only necessary. How do you know whether this is sufficient or not? Yeah, observability implies that it should be true, trivially in fact, but then we deduce something interesting. We said that if W2 0 implies W1 is 0, then this matrix R1 xi must be factor right prime. That was something that we that was pretty interesting, right? That observability will imply through the fact that W2 0 implies W1 is also 0. So, observability implies W2 equal to 0 should imply W1 also is equal to 0. This condition implies that R1 xi must be factor right prime. That is something special. Yeah. Why is that so? Because we have already done this before, but when you have these equations R1 xi W1 plus R2 xi W2 equal to 0, that is the behavioral equation. So, every trajectory W1 W2 in the behavior should satisfy this equation. In particular, if you insist on W2 being 0, this part is 0. So, now, so this is the situation. We have R1 xi acting on a W1 and it must produce 0 in order for W1 to be in the behavior, that is in order for W1 0 to be in the behavior. We must have this equation. So, that means this belongs to the behavior if and only if W1 is in the kernel of R1 xi, right. Now, this R1 xi is should necessarily be a tall matrix. You see, if this is G and this is Q1, then it should necessarily be a tall matrix, otherwise there are problems. You see, what do I mean by saying this thing that W2 0 guarantees W1 is 0? It means that in this situation this should imply W1 is equal to 0, but this implies W1 equal to 0 means that kernel of R1 xi must be the singleton 0, right, because if the kernel is non-zero, non-trivial, then there will be other trajectories W1 satisfying this, which means W1 need not be 0, right. In order for W1 to be 0, it is necessary that R1 xi is 0. The kernel of R1 xi is 0, not R1 xi, kernel of R1 xi is 0. Now, ask yourselves this question, that given a polynomial matrix, whatever be its size R xi, when is its kernel equal to 0? Can you give me an example of a situation when this guy has kernel equal to 0? You know already, if it is a square matrix and it is a unimodular matrix, then it is indeed, right. If it is a fat matrix, is it possible to have non-zero kernel? No, not at all. We have seen, right, that you can then divide it as P minus Q, then you have a transfer function equal to P inverse Q and so on, and there are infinitely many trajectories that satisfy that are in the kernel of this matrix. So, if it is a fat matrix, out of the question, it cannot be 0. If it is square unimodular, then it is true, then it can be. Secondly, if however it is a tall matrix, then also there is a possibility that the kernel is 0. And when is that? The kernel is 0. The kernel is 0 in fact if and only if this matrix is what is known as a factor right prime matrix. Factor right prime. What does that mean? Factor right prime means that if you write this matrix as an R0 xi times f xi, where f xi is square. So, here it will be q by q, this is again G cross q. The only possibility is that this is a unimodular matrix. If that is so, then it is called a factor right prime matrix. How do you prove in this case? In this case, the proof, if you go back to my last lecture, you will be able to see the proof, the proof that we have done. So, we say that okay, yeah. So, we just essentially prove that if it is not factor right prime, then there will be if R1 xi is not factor right prime, then kernel of R1 xi cannot be 0, it is more than 0. So, that contradicts the assumption that we have made that W2 equal to 0 implies W1 is equal to 0. Alternatively, if you want to see why FRP is necessary for kernel representation to be the kernel of R1 to be 0, you see, remember FLP? Likewise for FRP, for factor right primeness, it is necessary and sufficient that R1 lambda is full column rank for all lambda in C. Now, if it is full column rank for all lambda in C, then that means R1 lambda V equal to 0 implies V is equal to 0, right. If a matrix, constant matrix, this is all linear algebra, V now I am assuming to be a vector in complex number Q, right, Q sized complex vector. So, a constant matrix with complex entries, if it is full column rank, then when V acts upon it, it should produce 0. If it produces 0, then V must be necessarily 0, because its null space is 0, right. R1 lambda's null space is 0, it is a full column rank matrix. If you do not understand this, then just go back to your linear algebra studies, right. So, therefore, if it is factor left prime, well, if it is not factor left prime, if it is not factor right prime, if it is not factor right prime, then that means R lambda rank falls below its number of columns for some lambda, for some complex number lambda. That means the full row rank property, full column rank property of R lambda is lost for some lambda. Okay. In that case, it is possible to find out a vector V, let us say V hat, which is equal to 0, where V hat is a complex Q sized vector and V hat is non-zero. So, there is a non-zero vector V hat, and in that situation, notice if I take V hat e to the power lambda t, this is a trajectory, and this trajectory when gets acted upon by this matrix R xi, suppose R xi is not for factor right prime, when this acts on it, notice what happens. What does d dt do to e to the power lambda t? It just brings out e to the power lambda t. What does d square dt square do to e to the power lambda t? It brings out lambda square e to the power lambda t. Yeah. So, you see, for these exponential trajectories, the action of a differential operator is just multiplying that exponential trajectory by the same polynomial with d dt substituted by the exponent lambda. In other words, given a polynomial p xi, I am sure you know this already, given a polynomial p xi, p d dt's action on e to the power lambda t is the same as p lambda e to the power lambda t, you see. Therefore, what happens to this guy? What happens to this guy? This is just R xi replaced by lambda, V hat e to the power lambda t, but V hat is such that this is 0. So, that means this is equal to 0, which means this is a trajectory in the kernel of R xi. So, if R xi is not factor right prime, then there exists a complex number lambda such that R lambda is not full column rank. So, that means there exists a V hat in C q minus 0 such that R lambda V hat is equal to 0. It then means V hat e to the power lambda t belongs to the kernel of R xi, which means kernel of R xi cannot be just 0, cannot be just trivial. Okay. So, not FRP means kernel is non-zero. So, therefore, once again we reach the contradiction, the one that we wanted to prove, that W2 equal to 0 implies W1 is equal to 0. That should mean R1 xi is FRP, otherwise there will be trajectories W1 non-zero even when W2 is 0, right. Up to this much is fine. So, once again we establish W1 is observable from W2, that implies W2 equal to 0 implies W1 is equal to 0. This statement implies R1 xi is factor right prime. Then we wanted to prove that factor right prime implies observability. That means we should be able to deduce what is W1 from W2. Why is that so? I did that proof very quickly. Let me redo it. So R1 xi is factor right prime. Okay. So R1 xi being factor right prime means R1 xi must admit a Smith canonical form which looks like U xi and then identity of size q 0 V xi, right? All the sizes matches, all the sizes match. This is G cross G, this is G cross Q, this is Q cross Q. So all the sizes are fine. Okay. Now I do this following construction. Notice I have R1 xi here and I am saying that this is equal to U xi identity of size q padded with zeros, so that this is G cross Q times V xi. That is the Smith canonical form. I multiply this guy from the left by U inverse xi. I do the same here, U inverse xi, correct. Then this becomes identity of size G. So then the product actually is equal to just size IQ 0 times V xi. Okay, very good. Further I multiply this guy by IQ 0. Okay, so that this is G by G. This is G, this is Q, QG size. If it is Q and G size, then the product is, this is G by G. So the product is once again Q by G. This is G cross Q. So the overall product is Q cross Q. Okay. Now, so I must do the same thing here. I multiply this by IQ and 0. And remember, once again I take a tally of the sizes. This is Q cross G. This is G cross Q. This is Q cross Q. So the overall product is Q cross Q, right? This is also Q cross Q, so we are fine. Yeah, right. I think we are okay here. Right. Right. Okay. Now, what is the meaning of this product? This product, this is a Q cross G, G cross Q matrix. So it's a Q cross Q matrix. And you see the way I have written it, the Q cross Q matrix is IQ, and that multiplies V xi. So the result must be equal to V xi. Okay. Now all that remains to be done is multiply from the left by V inverse xi. V is a unimodular matrix, so multiplying by V inverse is fine. So that is the same as V inverse xi multiplying V xi, which obviously is identity of size q. So then what have we done? Look at this matrix. Yeah, this matrix is V inverse xi identity of size q padded with 0, so that it becomes Q cross G multiplying U inverse xi. This we define as R dagger xi. So then essentially what we have proven is that the way we have written R dagger, we have constructed R dagger xi, R xi is identity of size q. Remember, q is smaller than G, smaller than or equal to G. Okay. So the moment R is factor right prime, I was writing R1, so R1 dagger I should write R1 dagger. So the moment we assume R1 xi is factor right prime, that implies there exists at least one R1 dagger xi which is of size R Q cross G xi such that their product is equal to identity. Remember what is happening, it is a tall matrix R1 xi getting multiplied from the left by a fat matrix and producing identity of the smaller of the two sizes, that is number of rows here and number of columns here, that size. Have you seen such a thing before? I am sure you have seen it before, including in case of constant matrices, and I am sure you had called this guy in those scenarios, the analogous guy here that multiplies from the left, a left inverse, right. Sometimes also called a pseudo inverse, but left inverse is I feel is a more proper term because we are indeed multiplying from the left. So, it is a left inverse. Now, so whenever R1 xi is a factor right prime matrix, it admits a left inverse. I am saying A because there could be multiple, yeah, that will go to you as an exercise to show that there are multiple possibilities of left inverse given a factor right prime matrix. So, a factor right prime matrix gives a at least one left inverse. Okay. Now, what happens to that? What can we do with that left inverse? Remember, we have R1 xi W1 plus R2 xi acting on W2, that is my behavioral equations, right. This behavioral equation multiplies, if I multiply this from the left by the left inverse, yeah, then it should still satisfy this equation. So, here it is, W1 W2 belongs to the behavior implies we have this further implies R1 dagger xi R1 xi acting on W1 plus R1 dagger xi R2 xi acting on W2 must be equal to 0, but this is equal to identity of size q of size q1 here, yeah. I should have written q1 everywhere. This is q1, this is, so everywhere it is q1, yeah, q1 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 q1, oh so many q1s, q1 q1, I hope you get the point, q1 q1, right, yeah. So, size q1, which means now I have W1 is equal to minus of R1 dagger xi R2 xi acting on W2. So, we have W1. So, W1 W2 belongs to the behavior implies, when R1 xi is factor right prime, implies that W1 must be minus R1 dagger xi R2 xi acting on W2. That's an observable equation, isn't it? That's like a mapping from W2 to W1. So, no wonder we can observe W1 from W2. This is the relation given W2. If W1 W2 is in the behavior, W1 must be this. So, we can deduce W1 from W2. So, we have observability, which means we have proven this implication. Perfect. And if you like, this is our observer. Is it a good observer or not? That is a separate question, because usually you use Leuenberger observer and so on, because this has just derivatives, yeah. So, only differentiation we are doing. So, questions of noise getting amplified and so on, those problems will be there. I am not saying that they are not, they have been eliminated, though that question did not even arise here. What we have shown here is that there is a polynomial differential operator which acts on W2 to give you W1 every time W1 W2 is in the behavior. Whenever W1 W2 is in the behavior, if you make this guy act on W2, this guy act on W2, the trajectory that you get must be W1, yeah. So, we have the full circle, So, we have observability. So, we can actually list out properties of necessary and sufficient conditions for observability like we did for controllability. So, W1 so okay, let us start with the behavior. Behavior is given by all W1 W2 C infinity satisfying R1 xi W1 plus R2 xi W2 is equal to 0. Then the following are equivalent. The following are equivalent. Number 1, W1 is observable from W2. Number 2 is R1 xi is factor right prime. Number 3 is R1 lambda is full column rank for all lambda in C. Do we need anything more? I think this is enough. I can also add this one, no harm. R1 xi admits a Smith canonical form which looks like this. Okay, so that's observability for us. Now, whatever time is remaining, in that, let me try and introduce this this topic, which is kind of not directly related to what we would be doing in future, but it still is an important thing to remember because we have been discussing these ideas. So, the idea of relating control with controllability. Yeah? If you remember, for state space controllability, if you have an AB pair which is controllable, then it also guarantees that you can do arbitrary pole placement, right? If you remember, by state feedback. Yeah, if you have x dot equals ax plus bu and AB pair is controllable, AB pair is controllable. Yeah, then when you give this feedback x dot equals ax plus bfx, that is x dot equals a plus bfx. Then you want to assign the eigenvalues of a plus bf to arbitrary locations, and it is possible if and only if AB is controllable. Yeah, so eigenvalues of a plus bf can be placed arbitrarily. Well, we have to be careful when we use this word arbitrarily, because these are often assumed to be real matrices, and for real matrices I have to satisfy there are some restrictions on these eigenvalues of a plus bf, namely they should appear in complex conjugate pairs always, right, and these eigenvalues there should be n number of them, yeah, counting their multiplicities. So, those eigenvalues, so provided those conditions are satisfied, then the eigenvalues of a plus bf can be placed arbitrarily if and only if AB pair is controllable. Yeah. If you are not familiar with this, then please read up any book on any textbook on multivariable control theory. It will be discussed there, right. Now, what is the meaning of, does controllability, does behavioral controllability have a meaning similar to this one? For that, we need to first define what we mean by control. Recall R xi W is equal to 0, that is our typical description of the behavior, right. If we do some input output partitioning, after we do input output partitioning, possibly after permutation of the variables, we can write down the equations in this form: p xi minus q xi acting on y u should produce 0. Okay, this is, remember, G cross Q size matrix. When you give control, you put additional laws between u and y, right. Control is putting additional laws between u and y. So, behaviorally it means if this is your behavior, you have these variables, right, these are your w variables. When you put control, it means either you choose all these variables or you choose a subset of these variables, and on that you put another additional law and you call this the control, okay, and together is the controlled behavior. In our case we have p xi minus q xi, these are the equations for the behavior, the plant. The controller would put more laws, more equations involving those variables or a subset of them. So, those will be new laws, and together when both the laws are satisfied, that will be my control system, right. It is the intersection of these two behaviors, both the laws must be satisfied of the plant as well as of the controller. I also want that this system is autonomous, right. See, when we do state feedback, this becomes an autonomous system, isn't it? No input is there for, no further input is there, it is an autonomous system. So, the eigenvalues determine whether the system is stable or not. Okay. So, here also I need to make sure that it is autonomous. And what do you know about autonomy? We have seen in this course that autonomy means that this must be a square matrix of non-zero determinant. We will come to the non-zero determinant part later, but to make sure that it is square, how many equations should we have? We must have, so this was G, this is Q, right. So, this must be Q minus G, right. So, these are the new equations. The question is, where are the modes of this system? They are the roots of the determinant of this new matrix. So, pole placement would mean, can we place the roots of the determinant at arbitrary locations by putting in laws like this? The answer is that you can do that if and only if the system is controllable, okay. Behavioral controllability, that means this matrix P minus Q matrix must be factor left prime, okay. This and some more ideas about, some more ideas involving controllability is something that we will see in the next lecture, okay. Till then, take care, bye.